I've been promising you for a while that I was going to show you how to use antiderivatives to evaluate these definite integrals that do all these area calculations for us. And here it is. It comes from the Fundamental Theorem of Calculus, Part 2. And it seems strange to start off at Part 2 of a theorem. Part 1 is called Part 1 because you actually need Part 1 in order to prove Part 2. Part 2 is actually going to get a lot more use. We're going to use this all the time for the rest of the semester. And Part 2 is frankly much easier to understand than Part 1. So we're going to do Part 2 in the videos, and then we'll talk about Part 1 when we get together in Zoom. All right, so here's Fundamental Theorem of Calculus Part 2. It says if little f is continuous on the interval a to b, and big F is any antiderivative of little f, then the definite integral of little f from a to b is just that antiderivative, big F, plug in the upper limit minus big F, plug in the lower limit. So all I'm going to do in the videos today is a bunch of examples of using the Fundamental Theorem of Calculus Part 2. All right, let's try our hand at this Fundamental Theorem of Calculus Part 2. So we're going to evaluate the integral from 1 to 8 of the cube root of x dx. The Fundamental Theorem of Calculus told us to find an antiderivative for our function cube root of x. So the first thing I'm going to do is to change this into x to the 1/3 so we can do our antiderivative power rule. So I'm going to write this as the integral from 1 to 8 of x to the 1/3 dx. All right, so remember with antiderivatives, we're going to add 1 to the exponent and then divide by the new exponent. So I need to come off to the side and add 1 to my exponent. So 1/3 plus 1, or 1/3 plus 3/3. So my new exponent is going to be 4/3. So we're going to take x to the 4/3, then we're going to divide by that new exponent 4/3. So this is going to be x to the 4/3 divided by 4/3. Now, when we were finding indefinite integrals, we would always put that plus c on the end because we were acknowledging that there might have been a +7 or a -52 tacked on the end of the function before someone took the derivative. When you're finding a definite integral, you don't need to worry about that. If you go back and look at the Fundamental Theorem of Calculus, it just says f is any antiderivative of lowercase f. So I'm going to pick the one that doesn't have a constant on there because it's the simplest one. All right, so the next thing I'm going to do is take my antiderivative. I'm going to plug in 8 and I'm going to plug in 1 and subtract like the theorem tells me to do. Our notation for this is to draw this vertical line. And this vertical line is not an absolute value bar. It's a vertical line that kind of means evaluated at. So we're going to say evaluated at 1 and 8, and we're going to subtract. Let's see, before I do that though, let's simplify that dividing by 4/3. That's actually multiplying by 3/4. So I'm going to write this as 3/4 x to the 4/3. We're going to evaluate that from 1 to 8. All right, so we always do the upper limit minus the lower limit. So let's plug in x equals 8, clear off my scratch work. So I'm going to have 3/4 x to the 4/3. So I'm going to have 8 to the 4/3 minus, plug in the lower limit. So 3/4, 1 to the 4/3. All right, so let's clean that up a little bit. 1 to the 4/3 is easy, that's 1. 8 to the 4/3, let's see if we can figure out what that is. So I've got 3/4, that's the cube root of 8 to the 4th minus 3/4 times 1. I don't know about you, but I don't have 8 to the 4th in my head. And if I did, I probably wouldn't know what the cube root of that is. So let's go over to the calculator to figure out what that number is. All right, so I'm going to find 8 to the 4th, which is 4,096. And I'm going to find the cube root of that, which is 16. So I've got 3/4 times 16 minus 3/4 times 1. Normally I would reduce that 16 with the 4 in the denominator, but I've already got this nice common denominator situation going on. So I'm just going to treat that 16 as 16 over 1. And 3 times 16 is 48. So I've got 48 over 4 minus 3 over 4. So I can just subtract numerators. And I'm going to get 45 over 4. I've posted a link to this Geogebra Applet in the resources for the week if you'd like to use it to check your answers to these definite integrals. So it has an f of x and a g of x. This applet is going to draw and calculate the area between two curves. So I have my first curve as being x to the 1/3. That's our cube root of x function. Our second curve is y equals 0, or the x-axis, because right now we're doing all of our areas between a curve and the x-axis. And then I entered my limits from 1 to 8, and it's drawn the area for us from 1 to 8 underneath the curve cube root of x, and it calculated it for us, got 11.25. That's equivalent to 45 divided by 4, which is the answer that we got. Let's try another one. So we've got the integral from 2 to 5 of 1 minus 2t dt. Remember, the variable doesn't really matter too much as long as it matches the variable of integration in the dt at the end. So we need to find an antiderivative for 1 minus 2t. So what can we take the derivative of that gives us an answer of 1? Normally we would think of that as being x, but our variable is t here. So we're going to have that be equal to t. We know that the 2 is going to go along for the ride on the antiderivative, and we need to find the antiderivative of t. Remember, the exponent on the t is a 1. We're just going to add 1 to the exponent and divide by the new exponent. So t squared divided by 2. And then we're going to evaluate that from 2 to 5. So that's that vertical bar that says I'm about to plug in the 2 and the 5. Now I've got two parts to my antiderivative here. So sometimes I'll turn that vertical bar into a set of brackets. So it's obvious that I'm going to plug into both of those terms. Either way is really fine. All right, so let's simplify our antiderivative. I'm going to cancel out those 2's. So I've got t minus t squared, evaluate from 2 to 5. All right, remember, we always plug in upper limit minus lower limit. So plug in your upper limit. I'm going to have 5 minus 5 squared minus 2 minus 2 squared. All right, so the first one is 5 minus 25, so that's going to give me a negative 20 minus, and then I've got 2 minus 4. So in the brackets here, 2 minus 4 is going to give me a negative 2. So I've got a negative 20 minus a negative 2. And then that's going to give me a negative 18. Let's head over to our Geogebra Applet to look at a graph of this area and to check our answer. I'm expecting, because I got a negative answer, that all or at least most of this area is going to be below the x-axis. We have to change our variable over to x to get this applet to play along. So I graphed f of x equals 1 minus 2x instead of 1 minus 2t. And we can see our graph here, and it shaded the area between our graph and the x-axis. And it got the same answer we did, negative 18 for x going from 2 to 5. And like we expected, this area is below the x-axis. Remember, the definite integral is always going to calculate area below the x-axis as being negative area.